claim to fame, I guess, and why I got invited here is I do a lot of satellite remote sensing, mostly ocean color, to be honest, but I do a fair bit of sea surface temperature remote sensing as well. And Chuck asked if I would adjust some of my remote sensing stuff. I give a workshop every year at Cornell, mostly devoted to ocean color. I've done it for 25 years. So I'm going to present some of the sort of a cut and paste of a bunch of slides that I present. I also teach an intro ocean class. There's a few slides, kind of background slides on basic oceanography that I thought I would throw in a little bit later on in the lecture. It did it to us again. Just a second, guys. So I'm even not without technical difficulties here. So hang on, I'm going to escape for a second and stop. I'm going to stop sharing for a second. And for some reason, this thing doesn't like, it's very finicky, and I don't know why exactly, but it is. All right, so this is the outline today. So I have 2 days I'm here, and Aaron and I are both leaving Wednesday morning at 5 o'clock in the morning because Aaron's teaching this week actually, and I teach first thing Monday. So we have to get back, and I have to get back and get ready for that, and she has to get back and teach. So today it's all lectures from me today. This next 2 hours, we'll probably go for an hour and take a break and go another hour. I had set this up to be 3 separate lectures, and I just merged it all into one single file. So we'll go through this file to a certain distance in, and then we'll take a break, and then we'll finish off. I'm going to start with what I call remote sensing basics. This is a polar orbiting satellite. This is a geostationary satellite. This is raster image of satellite data, just some real basic generic stuff. And some jargon terms that remote sensing people like to use. There are certain terms that are LAC and GAC and level 1, level 2, level 3, and they're not super complicated, but it's nice to be given it at least once, so that when you run into some of these data source sites, you know, it's like, well, do you want level 1 data or level 2 data? So talk about that. And then the next lecture in this series will be more specific on SST remote sensing, and talk a bit about the remote sensing of sea surface temperature, and specifically the data set that you'll be working with tomorrow. And then this is where I don't know where everybody's, you know, coming from. And so I'm going to present, you know, a few, it's going to be relatively short, quick and dirty. This is Unix, and this is, all these Macs are Unix based. All these Macs have a Unix terminal you can pop up, and we're going to use some Unix and just a few commands of changing directories and listing files in directories, just a handful of things, and then some basics of Python. All your Python that you will learn in this class is going to be by doing it, you know, and I've got a nice handout for tomorrow, and it's going to say cd change directory, your data directory, by typing cd space return or something. So the lecture is just to get you broadly oriented, and Python is to get you broadly oriented about what is Python. And again, I'm not going to go through, these are all the functions. This is how you create a for loop, et cetera, that will be figured out as you actually do it. And then tomorrow we'll run some Python scripts that I've written already for you guys. One is a nice little script that will pull the data sets that we're going to work with. These are really popular data sets for marine heat waves, I've discovered. So I was not a marine heat wave person until Chuck asked me. So I'm like, which data? Because there's a lot of SST data products out there, and it's like, which one's the one to use? And it seems to be this OI optimally interpolated SST version 2.1 is a pretty popular one to use. So that's one we'll use tomorrow. I've got a little script that you give it a year, and it'll pull in all of the daily files for that year to your computer, so you can work with it. I've written a script that will plot the time series of whatever year you pulled over, and it'll also plot the 30-year climatology on for the same lat-long position. So you give it a lat-long position, you give it a year, and it'll plot a time series and the associated climatology and its 90th percentile, which is kind of the standard way of determining whether or not you're in a heat wave, or at least if it's a certain duration long. I wrote another one that just takes any SST, optimally interpolated SST for any given day and subtracts off the climatology. So you can sort of see the spatial distribution of anomaly. Yeah, optionally I added this extra thing that will pull this group high resolution SST data over its 1 kilometer resolution, up 25. So it's a nice data product, and it's super nice if you can pull over the subscene section of that data, because these are really big files at 1 kilometer resolution. And then if there's any time, I don't know, I was like, I don't know, I can't quite judge you guys and how much time this will take. This might take the full 2 hours to play around with. You can change years to your favorite year to do a time series, change lat long to do your favorite time series. So I threw in a few extra add-ons just in case there's extra time and people feel like they need to learn a few things. Those who are more advanced, you can just open up the code that I wrote and see what I did in that code and get an idea. And the hope is that when you guys do your workshop, this is very simple. The time series code just goes to one very simple or very specific lat long position and pulls the time series out for that position. You might want to grab a whole region and average that time series. So this script is a nice starting point with just one single lat long point, 1 pixel location, but you can modify this code, do save as, and make it my favorite time series code. And you can start to play games with of looking at broader regions and average conditions of broader regions. I haven't done that, but this is a nice way to expand upon that. Okay. So this is something to be, I'd like to make people all aware of. Is back in the 80s, there was a mission to planet Earth program that NASA created, and it's now called NASA's Earth Science program. And one of the really important points of that program, sort of first of its kind, was this idea of open source or rapid distribution of what do I call it? Immediate open access of all data. And years ago, when we'd go out to sea, we'd collect data and we would write our research papers. And once our research papers were all nicely written and published, we would make our data available. This was this idea of as soon as we collect the data, it's going to go out there and it's going to be made publicly available. And also in addition, so they created so NASA started with this and created a lot of distributed active archive centers. So they had experience from the past where they launched a lot of instruments, they collected a lot of data. It was sort of a lot of proof of concept missions. The data ended up just getting stored in a warehouse. The scientists never really got a look at it. So this mission to planet Earth was, let's rethink this. In addition to launching all this hardware, let's get a really good data archive center going. And let's get some nice web page interfaces going to make it really easy for scientists to get to the data and make use. And by that means we make this data really valuable. They're sort of, not to pick on the Europeans, but for the longest time, the Europeans were like, no, you must write us a proposal of your proposed research before we let you have your data. And if we feel like it's really good research, meanwhile, NASA's like, it's all yours, So all the papers that came out, starting with CBUS with Ocean Color, it's the one I'm most familiar with. It was like publication after publication after publication, CBUS, MODIS, Beers. And the Europeans, Maris and other Ocean Color missions, they got very little publications because nobody wanted to deal with this. Right. So finally, they kind of said, we're open access as well. So. All right, that's one thing. The other thing is there are these two sources of data that you'll find out there, NOAA and NASA. And traditionally, NASA was the science research agency. They developed new kinds of instruments, new kinds of calibration methods, and they were sort of the research and development kind of agency. And NOAA is the operational agency. Once a satellite is mature and the processing and the algorithms are mature, they take on the regular day-to-day acquisition and distribution of the data. So there's a lot of overlap there. Some of the data that, in fact, probably the OISST data that I mentioned before, you can get it from different sites, from NASA site, from the NOAA site. The stuff we'll work with is going to come from the NOAA site. But there are other data, the physical oceanography DAC at JPL is another site you might work with occasionally. The global high resolution, the group high resolution SST data is from the JPL Distributed Active Archive Center. And then this one is it's fairly new to me because I'm mostly ocean color, and I used to always go to basically the ocean color website, order their data, but this is now becoming the industry standard for NASA data. And we're not going to use that in this 2-week session, but I wanted to make you aware of this Earth data search site. Okay, so remote sensing basics, types of orbits. So there are 2 kinds of satellites running around out there that can collect SST. There's the polar orbiting satellites, which are probably the most prominent ones that you're going to come across most often. I've played around a little bit with geostationary data, but that was a long, long time ago. And I haven't really gone back to that since then, but they are available in 2 flavors. Polar orbiting satellites are going to orbit along the equator at the same rate at which the Earth spins, so it sees the same spot continuously. The nice thing about that is it sees at high temporal resolution. If you have clouds, it's a nice way to get a daily image of a cloud-free, relatively cloud-free a view of the Earth, because clouds are, you find out, are your vein. You'll be surprised maybe at how many clouds there really are out there. And that's true for SST. It's true for ocean color, but also SST. So geostationary see the same spot. Polar orbiting, they see the whole Earth, but they see just one snapshot a day, one fleeting moment of what that looks like. Here's how a polar orbiting sees the whole Earth. It's sun synchronous. Sorry about the blocking of the title up there, but sun synchronous orbit. It swaths out about 2 time zones, both SST, if it's infrared, SST 2 time zones, and it takes about 2 hours to make an orbit. So 2 time zones, the Earth spins 2 hours to go around the Earth. In that time, this satellite will swath out 2 time zones as they goes along. So you can imagine the sun in the back of the room there as things move around. So by the end of the 24 hours, it gets most of the Earth. This is a daily SST. You can see it's not perfectly daily data, because if you get to low latitudes, you'll have some gaps. The next day, the satellite will come down through those gaps and fill those gaps. Some places might be every other day. And then you also see lots of cloud cover, especially at higher latitudes, or wherever you have typical 60 degrees and intertropical conversion zone, you'll see quite a bit of cloud cover and gaps. But optimal interpolation is used. One, you can combine multiple data sources to try to fill in the missing data because of clouds, or you can optimally interpolate across these missing data areas to get these full coverage views of SST. Raster data. So I think it's getting a little bit dated now. I'll tell you in a few minutes the story, but 2 kinds of satellite. There might be more. I am not an engineer, and I barely know how the sensors are bolted together and designed and all that, but I know enough to just basically say there's sweep and push broom, and one moves north to south, and a mirror spins at high speed, and it's swath as you go along. So it's straight as it moves north south. And then this push broom one along track is to just have multiple sensors, detectors here, and to push along and collect a whole swath at the same time as you move north to south. Okay, that's all to say that no matter which instrument design you're dealing with, you're going to end up with a 2D array of values of some radiance, watts per meter squared, at some wavelength. If it's ocean color, it's going to be visible wavelengths. If it's infrared, it's going to be the IR wavelengths. Let's see, what do I want to say here? Each one of these little boxes represents some patch on the surface of the Earth. It's actually a solid angle. So right when they say it's 1 kilometer resolution, it's 1 kilometer straight below the satellite. When the satellite mirror points straight down and you see straight down, that's constant solid angle of view of the satellite. It's going to see 1 kilometer. It does stretch out because parallax to the side. So some of those pixels off to the side are going to be more like 3 kilometers, 2 or 3 kilometers. So they're not really 1 kilometer patch, 1 kilometer patch, 1 kilometer patch. They're roughly 1 kilometer straight below the satellite, slightly bigger off to the side. So this data, so here's my story. I did a postdoc at NASA Goddard a long time ago now, it seems like, with Chuck McLean And I got my first satellite image, you know, processed and printed it on this nice, beautiful this nice color printer. And I'm like, wow, this is, you know, really awesome. I've got my first satellite. And then it was like, what do I do with this? You know, and I guess I could write a paper that said, look how the chlorophyll is swirling down in this bottom corner and not so much up in the upper corner. And then I finally like, wait a minute. So that's just a pretty picture of what you really should care about. And that's the underlying 2D array. So, you know, when I teach this course in the summer, you know, they start right off with just basic Python. So you guys get 2 hours tomorrow, so you won't get too far, but it's 2D array, 2D array, 2D array, 2D array. Before they even see a satellite image in the workshop, they're playing games with 2D arrays of data just to learn the Python basics. And then they start working with satellite data and these 2D arrays of numbers. You're going to be all NASA data somehow, you know, headquarters. This was also a long time ago when I was a postdoc, where all the NASA folks, all the Goddard folks were grumbling that headquarters had ordered on high, I guess, NASA. Every NASA product will be delivered as HDF. Now it's CDF, but it's just a newer version of the same thing, same group puts this file format out. So all the different wavelengths that might be seen invisible, it's, you know, it's blue and green and red, and a few others for atmospheric correction in SST. If it was raw data, it would be, you know, radiance at 4 microns, radiance at 10 to 11 microns, 12 microns, infrared wavelengths. They get stored as separate 2D arrays. One is for wavelength 1, one is for wavelength 2, one is for wavelength 3. So they all get stored separately in a file, and that CDF file essentially. Yeah. And then from those files, those individual watts per meter squared per steradian, you're gonna, so per steradian meaning per solid angle of how much opening the satellite let light in. You can create higher order products. In this case, in this workshop, it's creating higher order products are going to be sea surface temperature. And you can add that in into your file if you wanted to, and you could have all the original watts per meter squared per steradian of different wavelengths and this higher order product that got generated by say, NASA group. Yeah, this is, I mean, it's redundant here, and but I'll just try to excite you, I guess. You know, it's just once I figured out that a satellite is not the pretty picture, that's like, so a lot of times when you generate these output from some scripts that I've written, not in this workshop, but in the other one in the summer, you output a netCDF file, but you also output a PNG, you know, and the PNG is rarely going to be used. You might use one PNG in a poster or one PNG in a PowerPoint, but that is not the thing you should be excited. I mean, they're pretty and everything, but the thing you should be excited about is the netCDF file and the underlying 2D array of numbers. And I say, you know, the early on in the I'm going to keep referring to ocean color because that's my thing. So you can translate to SST, but I'd read a lot of, you know, review papers, manuscripts that were kind of right after CWEP's launched the ocean color missions. And these people would write papers and they'd have all this satellite data, you know, PNGs in their manuscript. And notice how the chlorophyll is really high off the coast and how it's not so high, you know, and I'm like, would you guys do something more quantitative? Like, it drives me nuts, you know? So this is where you can be more quantitative, you know? So instead of saying, oh, the chlorophyll's higher over here than it is over here, notice how it's higher. You can grab all of the actual numbers, in this case, it could be degrees centigrade. If this was temperature, it's much warmer over here than it is over there. You can come over here, take the mean of these values, take the standard deviation of those values, take the mean of those values, and you can say with a p-value of 0.05, this place is definitely warmer than that place, etc. So all the math that you learned can now start being applied to do sort of hypothesis testing. You don't have to sit there and be qualitative and descriptive. You can be very quantitative once you start working with that data. Yeah.
So that sort of qualitative, if you look here versus look there, is that subject to like instrument artifacts? Like, could it be the case that you actually get it wrong?
Yeah, for sure. Yeah, in which case, both ways you'd calculate the wrong mean and standard deviation. So, you know, the qualitative thing, they both would be wrong at that point.
Okay.
Yeah. I won't get into it, but you can do tricky things with the color. So right now it's just grayscale and high and low, but you can do rainbow color bars where it's red and it's blue, but you can also do some wild color bars that that go for one color and repeat another color. I mean, you can get pretty crazy, in which case you could really start deceiving some people, you know, but choosing a color bar that you want. I call it the equivalent of when you're trying to create a plot. Suppose you're trying to create a plot that emphasizes a temporal trend over time. You know, you would not want to make a plot this wide and this tall. You'd want to make a plot this wide. It's the same data, but you make a different point and you draw the eye of the reader to a point that you want to make. So color, but we're not going to do color bar choices too much. We might tomorrow. I mean, if you guys want to play around with it tomorrow, because we are going to image some of the SST data. Okay, so here's just a few slides and we'll be done with this basics. And again, there's a lot of, so I used to tell students in this workshop that you guys are going to be mad at me by the end of this workshop because all these things that you thought were impossible to get past are not, they're not hard at all. The data is freely available. You don't have to have special anything. You know, you have to register as a user, but that's all you have to do. So data is freely available. You can process the data on a laptop. It's pretty easy to do that. You don't need some special high-speed computer to do that, unless you're doing really big things, I suppose. And so that was, I call them false, you know, phantom hurdles. You know, that is not, it should not stop you. The data is right there. Billions of dollars of data is right there waiting for you to pull over at your will. And then some of the other things are just some of the jargon terms that get to be a little bit, I don't know if it's intimidating, but it can stop you and go, you know, because these data sites, some are better than others, but a lot of them are just like, they're kind of, I guess, I don't know. Anyway, I find them kind of unfriendly. Some of them may, do you want level 1 data, level 2 data, level 3 data? And if you're new to satellite remote sensing, you're like, I don't, what's that? So, and they're not hard terms. And so I'll just walk through real quick. 0 is raw, just raw data. It's the number of photon counts on a detector on a satellite radiometer. Level 1A, it's the raw counts, and it has telemetry where the satellite is, you know, over the surface of the Earth, and the calibration to turn counts into watts per meter squared. And then there's another thing called level 1B. It's very similar to level 1A. It's just that they've applied the calibration table and the telemetry to the level 1 data, to the watts per meter squared per steradian. So for all intent, you're never going to see level 0 data. Almost never. I don't think you're going to. I worked with it one time a million years. First start of CWIFs, there were some problems with what they did from 0 to 1. And I had all this 1 data. I had to take it back to 0 with some software and then take it forward to 1 again with the right calibrations. So you won't be able to order level 0 data from a data source that I've ever seen. So level 1 data, for all intents and purposes, think of level 1 data as top of the atmosphere radiances, bottom line. Level 1, top of the atmosphere. Level 2, it's been atmospherically corrected and some algorithm to get watts per meter squared coming out of the ocean. And then from that, you're going to convert that into some geophysical product. SST in this case could be, in the case of ocean color, it's chlorophyll and CDOM and other things. So level 2 is geophysical, atmospherically corrected geophysical data, but it's still in the quote satellite perspective. Like if you were to project latitude longitudes on that 2D array that you display and you put lat lons on it, the lat lons would be, one, they wouldn't be going north south like this, they'd be tilted like that because the satellite doesn't orbit exactly over the pole. It orbits over the pole at an angle, so you'd see it tilted. And you'd also see it warped quite a bit because there's the curvature of the Earth and there's the parallax of the mirror as it goes off to the side. So it's still in satellite perspective. So 1 is top of the atmosphere radiances, 2 is geophysical, but it's still in that warped satellite perspective. And then level 3 has been mapped into this nice familiar, kind of grid that you'd be familiar with. And I won't go into much detail. If you're reducing the resolution of the data, you're going to spatially bin the data, and then you're going to map the bins. So anyway, you're going to work mostly with data sources that other people at either NOAA or NASA have processed up to this mapped data. And you're going to almost always be just working with this level 3 data. So you go to a data source site and they ask you if you want 1, 2, or 3, you're almost certainly early on, you're almost always going to say, I want 3, I want 3, I want 3. So, and if 3 can come in, do you want 1 kilometer resolution? Do you want, do you want 25 kilometer resolution? Do you want 1 degree resolution, long degrees? Do you want daily? Do you want weekly? Do you want monthly? Do you want annual? So the resolution is both space and time as far as the level 3 products go. This is another jargon term, LAC-GAC, LAC-GAC. LAC is local area. It's basically native resolution. Whatever the satellite can see, that's the resolution you want. And it makes sense. If you're dealing with something like the Gulf of Maine or something smaller and you're in a small confined area, you want the highest resolution you can get. 1 kilometer is really nice. If you're doing global scale stuff, you don't want 1 kilometer North Atlantic Ocean. It's way too resolved. So you want, quote, global area coverage, some sort of reduced resolution. So it all starts with full resolution, but then the folks at the different data distribution sites are going to create these final mapped products, these level 3 products that have been spatially reduced in their resolution so they're better suited for your research. So GAC is what you want if you're doing the whole North Atlantic or probably the whole Northeast Pacific, or the Pacific, yeah, Northeast Pacific. And so there'd be variable resolutions for GAC coverage. It could be 4 kilometers, 9 kilometers, 25 kilometers, etc. So there's no one fixed, what is GAC? It's this resolution. It's just reduced resolution. And there are a number of different levels of reduced resolution. Finally, oh yeah.
On the GACs, I'm assuming depending on what data source or satellite you'd be pulling from, it would specify, it would say if it's at 25 kilometers.
Yes, yeah, absolutely. Yeah, and yes, yes. Yeah, usually the data somewhere before you actually hit download, it would say minimally, because all this stuff you download is NetCDF, in addition to NetCDF having like array 1, array 2, array 3, array 4, it's got all this header information in it that has like this much on it's going to just scroll past your computer screen. We're going to work with this tomorrow of how was this thing processed, and it'll tell you it's 25 kilometer resolution. So every file has all of the gory details of how it was atmospherically corrected, etc., what version number it is, and everything else. Yeah. More information than you care to see, probably. Okay, finally, there's this. This is SST. This is not just SST, but SST and ocean wind speeds both use this jargon term, brightness temperature. And so instead of presenting their data, if you get into the literature at all in SST, where people are talking much about it in detail, you're going to hear some term brightness temperature. And all they've done is they've converted watts per meter squared per steradian. How wide open was the satellite? Was it really wide open, taking in a lot of radiant energy, or was it very narrow? So watts per meter squared per steradian. Actually, there's probably a per nanometer there. So much radiant. The spectrum. I've got one missing unit there. Nanometers of the spectra. But anyway, it doesn't matter. It's converted to brightness temperature, which is degrees centigrade. And I need one slide first, and then I'll tell you, it's a pretty simple idea, but let me quickly get to it here. So the dark solid line there is the perfect black body radiator. Everybody kind of remembers that from physics 101. But nothing's perfect. I'm not perfect. Close. I'm right about there. So anyway, so it's referred to as a gray body. So that's the radiance of something that's not a perfect black body. And the ratio of the radiance, that is the actual radiance at a given wavelength, divided by the perfect, beautiful black body radiance, is what's called emissivity of that radiance of that material, whatever that material might be, whether it's the ocean or the land or anything else. Emissivity is the ratio of the actual radiance divided by the perfect black body radiance, and brightness temperature is just the in situ temperature times the emissivity, and that's, if you want to just call it the apparent temperature based on the emissivity. If it's low emissivity, it's going to look like a slightly lower temperature. The satellite's going to convert the radiance into something that has a slightly less temperature degrees centigrade than the actual in situ temperature. So anyway, I wouldn't get hung up on this, but it's just a different way. If you see brightness temperature, maybe this is the best way to read it. It's just another way of presenting the same data. It's watts per meter. It's the radiant energy measured by the radiometer, watts per meter squared per steradian, and it's just been converted through this emissivity idea into what's called the brightness temperature. Okay.
What's the black body?
What's a black body? It's black. It's I think, Planck, so the Planck equation. So Planck, I think it's a body that every photon, no matter what wavelength, comes in and hits it, it's absorbed by that body, and then it heats up and starts radiating according to Planck's function, essentially. Yeah, which is an empirical function, by the way. So in fact, his empirical function led him to, we must have quantum states. I think that's the history.
So T brightness, which tends to be greater, T brightness or T in situ?
T brightness would be less than, because that emissivity is always less than 1. It can't be better than perfect.
Sure. Okay.
In most cases. Yeah.
But if we know the emissivity in the SST literature, wouldn't we want to be talking about T in situ rather than?
Well, yeah. So these brightness temperatures are not being, they're not being presented as that's the ocean's temperature. They will, instead of using watts per meter squared, and when we get to this is the next lecture now of the 3 SST specific remote sensing. The empirical algorithms that spit out the SST that you care about. They're, instead of using watts per meter squared with some empirical coefficients that are created by matchups with buoys, they're going to use the brightness temperatures instead of watts per meter squared. So brightness temperatures are not what are being displayed like that. That is in situ temperature using an empirical algorithm with watts per meter squared converted to brightness temperatures and then run through. And I don't know why they go through that extra step, but they do. So I'm not an SST specific person. So yeah. Is that clear? Yeah. So these brightness temperatures aren't like, oh my God, does that mean my temperatures aren't, your level 3 data is in situ temperatures. Yeah. Yeah. Okay. We can keep going. We'll just keep going.
How much do you have? Just we could take a little break.
Yeah, why don't we take a 10-minute break? I think we're probably even a little bit ahead of schedule, possibly, I think. So why don't we take 5 or 10 minutes if anybody wants to do the bathroom. It's kind of nice to break from one topic to another topic.
So
yeah.
You want to 10:45?
Yes, I will start at 10:45 exactly. Maybe 3 seconds early.
Yeah.
This is something that under because it's the same concept of whatever comes out, that's the max. So it's good to know like what could be, I guess, perfect in that sense.
Okay.
Or the total amount, and then it's never going to be like
This is how you come back.
yeah.
So this is what comes in.
Mhm.
But if you know the emissivity, this is how you actually plot CNC.
Yes.
So actually, maybe a more helpful equation is T in situ equals T
Yes.
brightness divided by.
Yes.
Okay, that makes sense.
Yeah, I think. Yeah, like, the concept is knowing like whatever is coming in. That's what's hit down. So you can't have a greater amount of what's coming in, what's going out.
That makes sense.
That's kind of how I just thought it.
Okay, so this.
Yeah. Yeah.
How do you know the emissivity of the gray body?
I think so. Earth has a general value.
And then what do you think of the latitude and ice and other things? Change that.
That's I don't know. Yeah. Also speaking from a thing like this mostly atmospheric, but I do understand like yeah, very latitude dependent. It depends on ice. It depends on what it's reflecting. Like yeah, if you have ice covered in of course so more or less.
Mhm.
So.
Okay. Thank you.
Yeah, I think in terms of like color, I think of it as like vegetation of the Earth's surface. So like if you have vegetation, then it will
Like sand.
yeah.
Like heavy tree cover is gonna absorb more potentially
Yeah.
than sand.
So like if you have an ocean, right? Say if this deep open water ocean is going to have a different emissivity than like say like marshland or something that's like less, you know. Yeah.
Very green.
Yes.
Okay.
Exactly. Oh, yeah, I took one ocean color class.
Really? Was it cool?
Yeah.
That was cool.
It was interesting, yeah. I feel like it was definitely on my purview. It was more like observational, but it was really great.
I just thought it was funny. He's like, and you all know about body from this.
Oh, yeah.
And I'm like,
Well, it's good. Yeah, well, it's good because well, my presentation I talked about Earth not being a black body, so I was like, oh, this is interesting. But I was like, yeah, this is so big.
I remember the first day of like high school physics because I had changed schools. And I got to this physics class and the professor was like, you all know F equals MA, so I'm not even gonna go over it. Anyway, moving on and over like, no, wait.
So we knew to
We don't know.
tell me new. So honestly, this
That's what we like.
Yeah, we like her
That's actually why we like her. You know?
because she was perfect. Then, you know, everyone in the as fun of a place to live.
Yeah.
You know?
Yeah. So, these emissivity constants,
Yes,
where do we find them? Where does one, not really.
you don't need
But
them.
someone else in the room.
That's a good question. I don't know. How's that?
But Anthony was explaining, like, for example, out in the deep ocean, you're gonna have a different emissivity constant than like the coastal.
I think, my guess is that I know for, in the case of passive remote sensing of ocean winds, they're variable by wind speed. That's the key to measuring, you know, so if it's a rough ocean or one with foam on it, it's gonna have a different, in the microwave, different, but my guess is that, so when I did my, whatever, my B exam or whatever it's called, my, you know, the final exam where it's the last exam before you go on and defend your PhD, and it was all these, you know, my whole committee's in the room, and you know, by the way, so anyway, so you stand up there, and if they ask you questions that you know a lot about, they're like, okay, let's move on really quickly.
Yeah, yeah.
And then when you get in a place where you don't know much about it, they keep you there for a while.
No, they got you, yeah.
And so I'm always drawn back to that room. when anybody asks me a question, like it could be intro ocean about, what would happen if this happened to the ocean? And I'd be like, so when you're in that, you can't just say, I don't know. Next question.
Yeah.
No, you have to like try to put two and two together. So when you're,
I'll get back to you.
yeah, so when you ask me this about emissivity, I'm like, well, so I'm back in that room again.
Yeah.
It's like, my guess would be that emissivity in the IR range doesn't change much, or you'd be reading a lot about it, and somewhere in the, in the stuff, the literature that because I'm an oceanographer, and then I decided to do, I have to read up on all this stuff and figure out how it's put together, and I've never come across anything in the IR field where emissivity is
Very
yeah,
likely.
Yeah.
Okay.
yeah. So my guess is that it's pretty constant. And I think it would show up as a problem if you put the brightness temperatures into an empirical algorithm and it had all kinds of noise in it because the emissivity is all over the place.
But for sure over ice.
Yeah.
It's gonna be.
Yeah. Oh, of course, yeah,
Yeah.
for sure. Yeah, so I will Google somewhere. Does the emissivity in the 11-12 range vary over the ocean vary? You can search that. Let me know.
Yeah.
Okay.
It's probably varies just on the color,
Yeah.
not just. of the
Well,
surface,
but I don't.
throughout.
No, I think it's for IR range. I mean, for visible range, I don't even know visible. I never even heard of emissivity for visible range. And it could be, that black body curve. Maybe it's down near the end where it's one and the same. Emissivity is one everywhere. On a certain ones. And maybe that could be for IR as well. And if it's only when you get into those longer places that it might start to deviate where you really have to pay attention. And I think that's in the microwave for sure. And I've almost never dealt with IR. Almost never dealt with the microwave SST. We'll talk briefly about it today, but I am not very familiar with the algorithms because almost all the stuff that I've ever worked with is infrared. SST. So I think it's by far the more popular science. One is you'll see in the slides. There's pros and cons of this in the microwave range. It's transparent to clouds. So the microwave emissions can go right to the clouds. You don't lose on it.
Next time you're gonna be.
But the emissions from the warm earth and the microwave wavelengths is really tiny. So it's near the basement detection level of an instrument. So when you'll see it in this like
Well, not all the way back.
in situ observed SST against the estimated satellite. It's a fairly tight fit with IR, and it's a pretty microwave. So transmits through the clouds. That's really cool. I don't know if today's data due to clouds, but at the same time, it's a really noisy signal that you get.
Is there longer? Is there longer?
Yeah, the curve peaks at about 11 or 12. On a warm Earth, the emissions is around 11, 12 lifetimes, and then it declines on either side.
I have just a quick announcement to follow up on an inquiry we had.
Yeah, 15 seconds.
Great, I'll go quickly. These snazzy new computers do not serve as extra monitors. There's some function that Apple changed, so they are standalone computers. If you want a smaller monitor to take to your dormitory room and use them, let me know. We'll get you squared away, but these ones are just computers.
Yeah.
Oh, at the time, is it time? I'm 15 seconds late. Dang it, man. Okay. So part 2 of a 3-part series, and this part is remote sensing, but it's specific to remote sensing SSTs. And I don't know, I put this, so here's the outline, some motivation. So I don't know, I have a hard time. I actually already did it. I jumped into remote sensing basics in the summer workshop that I run, I usually start with this thing of what I call motivation. It's actually a whole hour of what things can you do with, ocean color satellite stuff. And I have a few slides here that I just couldn't resist putting in to kind of motivate everybody and get them excited about the idea of remote sensing SST and what might be possible and what's the value of it, I guess. And then we'll launch into sort of the details of satellite remote sensing, infrared versus microwave methods, skin temperature versus bulk temperature. So the satellite, you'll find out, sees what's called skin temperature. It's the upper micron or millimeter of ocean water, the temperature of that upper little skin layer. And then I'll briefly say a few things about this OISST data, this data that is commonly used for marine heat waves these days. We're not going to work with that, this heat waves analysis software, but there are some analysis software that will generate, how many consecutive days we're above the 90% percentile and all that stuff. And I don't, an older version of that software is written in Python and the newer versions are written in R. And I'm not really an R person. So I just wanted to make you aware that these analysis packages exist, and you can install those packages if you want and run with those especially if you are experienced. Okay, here's my motivation. These are some of from my intro ocean kind of class of talking about climate change. So we've dumped a lot of CO2 waste into our atmosphere, raised concentration of CO2 by 50% since the beginning of the industrial era. I'd like to point out that half of all the CO2 we have in the atmosphere today was put in there since 1980. So it's not like we had 150 years to make this problem happen and we have that much time to solve it. We have no time to solve it. This is I'd like to, I can't resist this. So once I get something in my head, I just cannot not say it. Yeah, Aaron knows this. So and my intro, this is just to kind of blow your mind a little bit. Okay, so that's 800,000 years of CO2 up and down, up and down, up and down, right? And naturally it's 180, 280, 180, 280, 180, 280, and now we're at 420. When it was down at 180, we had an ice age, and when it was at 280, we came out of an ice age and down to 180, ice age, out 280, out of an ice age. So James Hansen wrote a book about more than 10 years ago, maybe 15. It was the storms of my grandchildren, the coming catastrophes of climate change or something like that. And he made an offhand comment that as long as we have a functioning human society, we will never, ever have another ice age. That humanity has become powerful enough to stop an ice age. And this graph shows it, because we can't get an ice age unless we're down to 180 and we're at 420. So we can stop an ice age. That's what humanity has come to, So we have to get a lot smarter with what we do, because we've become too big and powerful to mindlessly move through this planet without thinking about the consequences of it. So that increased CO2 has created an energy imbalance, a 2 watt per meter squared energy imbalance. We now have 2 joules of heat energy per square meter coming in every second, and that 2 joules per second accumulates second by second, minute by minute, hour by hour, year by year. And that steady accumulation of that watts per meter squared, 2 watts per meter squared over time, has increased the temperature of the Earth to 1.17 degrees centigrade. And we all are aware, obviously, of the 1.5 that we'd like to limit ourselves to. And then the outsized role of the ocean, 93% of that heat imbalance, that energy imbalance, has been taken up by the ocean. And that has consequences of increasing the frequency and intensity of marine heat waves. And this is distribution of them. I guess we're going to have some lectures later on about the Northeast Pacific heat wave and its consequences. I just will say real quick that the little bit that I've read about the consequences of this Northeast Pacific one was decreasing primary production. Again, I am not the expert, so I'm waiting for somebody to say, Bruce, that is all wrong. But I'll say it anyway. Reduced primary production, shifted the zooplankton to smaller, less nutritious species, and then the small fish weren't as abundant in all the sort of trophic, not trophic cascade, literally, of classical sense, but of the impacts of higher trophic levels. Coral reefs. Shoot, I have all this. I thought I turned off all the notification stuff, but I'm stuck with that for the rest of this lecture, I guess. I'm afraid to move it off or we're going to lose this. So, okay, coral reefs, extremely, again, talking to the choir here, but we're all from different backgrounds, so I can't really. So 1 degree centigrade above their kind of climatological expected temperature. So some corals are acclimated to slightly cooler temperatures, some are acclimated to slightly warmer temperatures. And if you go 1 degree above for very long, if you went a day above, it's not a big deal, but if you go extended periods of time, and you're going to get a whole lecture on this, I think, from Mark Aiken later, then the zooxanthellae, so the corals are animals with guts, and they eat zooplankton, but they also have the symbiotic algae in the tissue, which gives the color to the coral. And when the zooxanthellae symbiotic relationship breaks down, the color, along with the zooxanthellae, the color goes away, and we have what looks like bleached. If it cools back down, they can regain those zooxanthellae and continue to live. But if they stay extended a period of time of elevated temperatures, then they die before they can regain that. And then the NOAA Coral Reef Watch program has been, sort of around for quite a while now, and is highly regarded by coral reef managers as a really important tool for monitoring the potential for coral bleaching of these coral reefs around the world. So this was a slide I presented in the intro ocean class back in 2015-16, when the time series of global warming went up to here. Every time we have an El Nino, we have this global warming. And, if we had El Ninos in the past, they have, this spike in warming, but it wasn't a big deal to the corals because they weren't right up on the borderline of crossing. But we've inexorably risen up to now. Whenever we have an El Nino, they cross that threshold and start to bleach. And in 2015, 2016, we had coral reef ecologists in tears as we watched their beautiful corals go bleach out. This is one of the Coral Reef Watch products that shows the 2015 extreme bleaching alerts for different parts of the Earth. And then we had another one just this last year, another El Nino and another big bite. And NOAA put out just back in April that, yes, indeed, we now have had a 4th global coral bleaching event. So we're going to have them, every El Nino now, all into the future. Corals are bleaching everywhere, every corner of the Earth, threatening its web of life. So this, some of you might be aware, this is kind of like the IPCC equivalent for biodiversity. This report compiled, state of knowledge of biodiversity by, peer reviewing all the peer-reviewed literature on biodiversity. So think of it as the IPCC equivalent of biodiversity. And in that report, it states that there's been a 50% decline in coral reefs over the past 150 years, and a 30% of all coral species today now are at risk of extinction. This is a paper that predicts in the next several decades around many of these coral reefs, you're going to see seasonal bleaching. Every time summer, and there's a little bit of a warming increase in the summer, you're going to start to bleach these corals separate from the El Nino parts. I don't have a slide here. I took it out because I didn't want to depress you, but I might add too much coral here. But, the IPCC special report on the difference between 1.5 and 2.0. In a 1.5 world, we're going to lose 70 to 90% of the corals. And in a 2.0 world, we're going to lose essentially all the corals, not greater than 99%. So we, are faced with some daunting challenges here. And in my intro ocean classes, every so often a generation is called upon to do something extraordinary. And we are really called upon these days. And, as Earth scientists, you guys are in this great place of being truly heroic, of figuring out what is coming our way before it fully arrives, and maybe we can avert some of these things. So.
Under the surface.
Yeah.
How you observe the coral conditions?
Well, so satellites are a real challenge to get coral bleaching directly, with observations, because 1 kilometer, these coral, the structures of corals are at much finer resolution. So a lot of the stuff that I've read about has been done by airplanes with imaging radiometers on airplanes that get high resolution. And then you may have a chance to see, white versus colored coral bleaching, or direct in situ measurements are the ones that are commonly used, surveys to measure the extent of coral bleaching.
Just to clarify,
Yeah.
to expand on that.
Yeah,
If you go
please.
back to the Coral Reef Watch maps, those are showing temperatures that are known at which corals would be at risk, right? These are showing
Yeah.
temperature alerts, right?
Yeah, and I didn't, again, Mark's going to talk about this, but this is based on what's called degree heating week.
Right.
Yeah, I should say that. So if you're 1 degree above your acclimated temperature for a week, you have a 1 degree heating. If you're for 2 weeks at 1 degree above, it's 2. If you're 2 degrees above for 1 week, it's 2. So it's a basic metric that in a very simple way incorporates how much temperature above and for how long it's been above.
I'm not sure if this is what you're asking again, but I mean, what we're looking at, this is a data product from sea surface temperatures.
Yeah,
And that's not exactly the temperatures
Yeah.
of the corals you're seeing.
absolutely.
Right.
Yeah.
So,
Sorry.
they often correlate
Yeah.
well with them, but there are places where they don't.
Yes.
And then you need to have the in situ temperatures.
Yeah.
To,
Yeah, if there's lots of mixing, maybe you get temperatures that are equal to the SSTs, but if they're not mixing, maybe they get this cooling refuge. Yeah, definitely. Yeah, way up to go below the skin surface of SST and infer what's going on a little bit, even a few meters below is going to take some empirical, and if you want to go deeper, it's going to take, something even more in situ measurements or some other inputs of how much wind speed you have or something like that. So there's a lot more to go further down below the skin temperature that the satellites provide. And I think Aaron probably talks a little bit about what happens deeper under the surface with some modeling. Yeah. Okay, there we go. Okay, estimating. So finally we can get past on. Is it inspiring or depressing? I don't know which it is. I mean, yeah, I know. Yeah, it's in my head again. So you're going to find out I'm pretty random. Hopefully in a fun, entertaining way, because I feel like when I lecture, one part of it is to give you the data and the facts and the numbers, but it's also to keep you awake and keep you entertained. So I hope I have the right balance here. So yeah, anyway, yeah, I say to these intro ocean kids, that I think everybody would like to be a hero. Almost everybody. There's some people who are really deranged, most everybody would love to be a hero. They just never were on the edge of the platform of a subway where somebody fell down and you got to jump down and pull them out. But we have been given, when you feel like you're at your most depressed, you can also say we're on the edge of the subway and somebody's fallen over, and we've been given this finally, because you can spend your whole life going, I wish I could be a hero. And what, you read somebody, there's a Cornell student actually that was in New York City that somebody fell down and undergrad and he jumped down and got him up. So I'm like, I wish I could have been there. So I could have done that and got, in the newspaper or whatever. So anyway, we are scientists. And, all this depressing stuff, we have been given an opportunity to be heroic to fix this problem, and, I tell students too that, as a generation, if we fix this problem, this problem will linger, 1.5 and 2 will linger for 1,000 or 10,000 years. And, I say that if we fix this problem, they are going to build monuments and write epic poems retold again and again, celebrating this generation. Or if we don't, they're going to be really, really upset with us, like really, really upset that you saw this, you had this chance, and you didn't take it. So we get to be heroes, guys. We're on the edge of the platform, and this is cool. Like we always wanted to be a hero, and now we have a chance to be a hero. Figure out some of these problems and fix them. So, okay. Yeah, let's see. What do I have? Estimating satellite from radiance measurements. Yeah, this is just a real quick. So this is, I knew there was a big difference, but I didn't realize this was this big. And this is, compiled in situ data between 1955 and 2012. And over that time period, what was the annual? So once, per year, how many SST measurements were made? And on average over this, whatever decades, 6 more, I don't know, I can't remember. Anyway, over all those decades, annual number of measurements per year, 1 to 2 SST measurements per year here. The green, 2 to 10 over the whole 365 days, 2 to 10 measurements were made of SST by in situ. And then a few of these got up to 30 or 50 or, so at the very best, you got a third of the total 365 days, you got about a third, about 100 days of actual SST measurements. So very limited spatial temporal coverage when you're working just exclusively with in situ data. So SSTs offer you this opportunity. You can, I don't know if I can do this. I'm going to try to hit that right now. Yeah, and then I can get rid of that. Good. Okay. Good. That was getting kind of too much. So, okay. So this is 1 day of a blended product of probably multiple satellites, and also buoys, and floating, both moored and floating instruments. See, this is what I was afraid of. When I click on this stuff, then I lose my ability to. So guys, I'm gonna have to exit the share just for a second. I'm gonna come right back in. Okay, so hang on. And then all I'm gonna do is restart the share, and should be good to go as soon as I pop this up. All right. So that's 1 day. So the 2 methods to measure SST. One is infrared. That's, in my experience, it's the most widely used method for getting SSTs. But there is another method, microwave method, that you'll read about and come across. And so I'm going to just briefly mention the difference between these two. So both are relying on measuring the radiance at a particular wavelength. In the case of the infrared, they're measuring it somewhere between the 4 and 12 micron, the thermal infrared wavelengths. And in microwave, they're measuring things out. Usually in the microwave literature, they recast just like brightness, temperature. These guys, some people, anyway, in frequency, so gigahertz oftentimes, but it's somewhere in the 1 to 10 centimeter wavelength range for microwave emissions. Okay, so in both cases, watts per meter squared per steradian per nanometer. I should have mentioned that before, but okay, so this is kind of the important slide on seeing the distinction between the two. Though actually, the next slide will also show. I'll show real quickly. Go to the next slide. Sorry, I should have switched this order. The nice thing about microwave emissions is that they're transparent to clouds. They can go right through the cloud, so you don't have all that data loss because of clouds. So that's the big, like, wow, that's super cool. Why doesn't everybody use microwave? And in the case of infrared, you have a lot of data loss wherever there's heavy cloud cover. You're going to have data loss. So the advantage of the microwave is transparent to clouds, and the disadvantage though is on this slide, which is let me go back. I'm sorry to be going back and forth, but this is black body radiation at the Earth's surface. So there's 285K per. That peaks somewhere in the 10, 11 micron range. That's the thermal emissions for a black body at Earth, 20 degrees centigrade or so temperature. But microwaves are way out here in the centimeter, so they're way out on the right side of that curve. And so this dark filled curve, the bottom. Well, you can look at the top curve. That's the clarity of the atmosphere at different wavelengths. And when the white goes all the way to the top, that's transparent. And when it's not very high, it's not very transparent. And in the thermal range, there's a lot of maybe 50% transmittance in some of these ranges of where do I have this? What they have? Oh, they have that as frequency. Oh, below they have as as infrared. So 10 microns in the thermal, and the microwave, the centimeters. So at the far right, you see in the microwaves, it's the atmosphere is all transparent. And in the IR, the 11, 12 micron range where the Earth emissions are peaking, the atmosphere is not very transparent, not as transparent. And then the bottom one is the point I want to make on this slide. The left side dark filled curve is the emissions of a 285K black body. And the right side is, go way out to the centimeter where microwaves are emitting. And that is, you can't read that from the back, and I should have just written it in big font, but it's that scale is times 10 to the 6th. So it's way, the signal in the microwave, the emissions, the natural emissions off the surface of the Earth in the microwave are 1,000,000 times less strong than they are in the infrared. So they're very weak signals. So this is a plot of in situ buoy data against microwave-derived SST. And this is, the top figure is buoy SST, so in situ ST against infrared derived. And you'll just see that the tightness of the scatter about in situ is a lot tighter on IR because the signal's a lot stronger. Even though the transmittance, is weaker, and you got to deal with atmospheric correction issues more strongly in that case. Because the signal is 1,000,000 times coming straight from the very surface of the ocean, is 1,000,000 times weaker in the microwave, you're going to get a lot noisier signal from that. Your basic signal is right near the basement detection levels of the instruments. So, this slide, again, you get good coverage. And I also should add that if you're interested in something that's LAC data, meaning full resolution, and by that I mean if you're thinking, so LAC data for infrared is 1 kilometer, typically 1 kilometer spatial resolution. So if you're dealing with small scale stuff, Gulf of Maine or something, and you want 1 kilometer, then infrared is what you want, because the LAC data, the local air, the native resolution can't get better than this of microwaves, is 25 kilometers or 35 kilometers, something like that. So it's a lot lower resolution. It's dealing with these longer wavelengths, so it uses another method rather than optics to make that measurement. And it produces these much lower resolution. So fine for global, kinds of studies, these microwaves, I suppose. Still keep in mind that they're going to be noisier than infrared. And they're going to be reduced spatial resolution. You're not going to want to use this stuff for fine scale stuff.
So are they doing that because they need a larger area? Since the signal to noise ratio is lower, they're needing to average over.
Yeah, I think, well, it's because I think they're using something equivalent of a trend. They're not using optics and bending and focusing, down onto small things. They're using antenna. I'm just on top of my head thinking of bioacoustics, and they're trying to measure the returns equivalently what the bioacoustic sensor would measure with side lobe stuff and everything else. That's the issue. Yeah. Like I said, I'm not really the microwave person, honestly. I know enough to know I don't probably really want to use it too much because of its scatter and its spatial resolution.
I'm just curious, as someone who's not very familiar with remotely sensed temperatures like this, is it kosher in the field to mix IR and microwave data products? Like I'm looking at Indonesia, and there's some points with IR, but then more coverage, they could combine them.
Yeah, you can. Yeah, well, people at data centers have provided that kind of blended product that puts the two together. Yeah. Again, I'm not super. I'll show you a table here in a second from a publication. Some of these, tables that I have that have the different sensors and what, is it a combined IR and microwave? They're in your reading list. In your home directories on these computers is a reading list, and you can read the fine details on these products in more detail. But yeah. Okay. So skin temperature. So let's just look at the left. The red and the blue are just the depth over which the temperature is being measured by an infrared sensor versus a microwave sensor. And the only real point here is infrared has a much thinner skin temperature, range over which it's making that measurement of that temperature. Microwaves kind of, average over a little bit thicker, meaning a millimeter. So I should say a little bit thicker. They're measuring about like that, the temperature in this volume right about here. And the infrared is measuring something on the scale of a bacterium or something close to that. So, so infrared is super, thin, and microwaves are not much, thicker than that. I mean, they're 10 times thicker, but that's not saying much. And all, and then, what you would actually care about bulk temperature, the skin temperature is going to be cooler than, so what the satellite actually can physically measure, the skin temperature is going to be cooler than the bulk temperature that's a little bit below that skin. When they, ultimately these relationships between watts per meter squared or brightness temperature, whatever unit you want to use, they're going to be empirical algorithms that are with empirical coefficients that are adjusted to give you a bulk temperature rather than this skin temperature. Let's see. I would say too, I mean, so here's the other problem with, there's probably, I don't know beyond these empirical coefficients, there's a wind effect on this thing that you can see, and if it's a calm condition, you could have a pretty big difference between the skin temperature and the actual bulk temperature versus a windy day where there's not as large. So again, needing to have external information to get a better measurement of what's going on actually at the depths that organisms would actually care about is a challenge.
So this is, I don't know anything about this. I'm learning a lot right now. Somewhat counterintuitively, I would have thought that like the temperature at the surface of the ocean would actually be warmer than the temperature like 3 meters down. But what I'm taking away from this graph is actually no, the first 10 centimeters of the ocean due to wind tends to be cooler.
I don't know that the wind is causing I don't know that the wind is actually this is calm condition or windy conditions, and there's not a big difference between the two. I think it's because there's some element of turbulent mixing that brings those two temperatures closer together.
Okay.
And when there's not, I don't think it's less cooling the surface. I think it's more adding turbulent mixing and mixing the warm little microlayer into the deeper parts of the, you'll see references in the literature to 4 microns and 11 micron or 10, 11 micron measurements. So there's two areas of the infrared that are used, 4 micron area, and then the 10 to 11 to 12 micron area. The 4 micron area is kind of special. The 11, 12, or 10, 11, 12 micron method can be used day and night, day and night, day and night. So 11, 12 micron day and night, 2 bands, 11, 12, 10, 11. And this 4 micron band can only be used at night because the solar emissions, that black body radiation, so direct solar emissions can be strong in 4 micron range that will contaminate that measurement during daytime. So it's not used during the day, it's only used at night, the 4 micron. This is reminding you of the black body 485K, and this figure is kind of a nice one to show you the problem. So the wide curve on the right is it's the emissions, the black body thermal emissions, and then the other curve, the short peak curve there is the solar, basically the solar input. And when you're out at the 10, 11 micron range, it doesn't matter if it's day or night. There's no solar influence out in the 11, 12 or so micron range of the spectrum. When you get over to here, you can use those wavelengths day and night. It doesn't matter. But when you're using the 4 micron wavelengths, you cannot use it during the day, because during the day, you're going to have these emissions from the solar contaminating that 4 micron emissions that is coming off the surface of the Earth. This is, I'm not really super familiar with, this is a new term. So I've definitely heard, the difference between skin temperature and bulk temperature. And there's another temperature separate from that, which is called the foundation temperature. You're going to have diurnal heating and cooling, daytime warming and nighttime cooling. And these colored curves are the rise and fall over a 24-hour period of your measured. This could be measured bulk temperature now, just a meter or so below the surface. So not the skin temperature, but that temperature a little bit below the skin. In this case, it's referred to as subskin temperature. Okay, and there's a third temperature that is referenced in some of the literature called the foundation temperature, and that's the temperature that doesn't undergo the seasonal oscillations, the diurnal heating, cooling that you see there. And to get those, as they state in this paper, so all these slides that I put up that have some comment like this has got the links to the reference to the article that talks about this stuff. So, and I think all of these things like this figure and the previous figure are going to be, or all the figures are going to, if there's a URL there, it's probably in your suggested optional readings in your home directory.
So this basically gets to the point that we talked about before. If you're looking deeper in the water column.
Yeah, you're going to need a lot more information to get
Right,
to.
and this enables you, if you have those measurements over the year, day by day, then you can actually adjust for it so that you get this foundation. You want to use this foundation sea surface temperature because the skin one isn't giving you exactly what's relevant to the biology that you're doing, for example.
But again, this is kind of a little bit outside of my wheelhouse. So I'll just say a few things. Let's just say, if your satellite is always measuring nighttime, I guess that would be fine. Maybe if you measure nighttime, you'd always have something close to what you would call the foundation temperature, because satellite data products can be nighttime. So the satellite, when it's ocean color, you get one snapshot when it comes around, and then it comes on the backside, and you get no data for ocean color. But for infrared, you get the sun side of the Earth, and then an hour later, you're coming up the backside of the Earth. So you can get a daytime snapshot, and you can get a nighttime snapshot on the opposite side of the planet. But over a 24-hour period, you're going to have a 2D array global of daytime and a 2D array global of nighttime temperature. So you might be able to figure out day and night some of the ups and downs. This is like continuous. This is probably in situ observations. I don't think this is satellite because it's too fine resolution. But you get the idea. Yeah.
Result is more close to the right line or to the.
I'd say the satellite result would be, it would be a snapshot, right? It sees if it's polar orbiting, it's going to see that, and 24 hours later, it's going to see that, and 24 hours, it's going to see the same. If that's where in this whole cycle of warming and cooling, this is at whatever hour, it's going to see that 24 hours later, it's going to see the rise and fall. Yeah, I think I don't know if I got your question quite right, but I would say that the skin temperature and the bulk temperature just below the skin is going to rise and fall like that, and then separate from that is this what's called foundational temperature. And I don't know what the depth range that would be, like how much deeper is that being influenced? At some point, there's no influence of the rising and falling of that temperature. Yeah. So water shallower than some depth here. This is not depth, obviously, but there's some depth at which the daily temperatures aren't going up and down, up and down, up and down. That's the foundation temperature. And there's some depths at which they are rising and falling, and there's the skin temperature will rise and fall, but the bulk temperature that's still in a range above that foundation temperature depth is going to rise, maybe not as dramatically day by day by day, it'll be attenuated, but will still rise and fall.
So, in other words, tell me if I'm correct about this, so the foundation temperature actually corresponds to also the skin temperature that the satellite's measuring at night after.
Closer, yeah,
After they've come into sort of, after the other part is cooled off, right? After the
there's a lot,
the
yeah.
thermal.
Yes, if I was going to work with this data, I would work with nighttime data. Yeah, just because people argue back and forth about, you know, day versus night, day versus night, day versus night, and I've always just stuck with night because I felt like it gives you a better estimate of the actual bulk temperature. Yeah.
Hey, Bruce.
Yeah.
On your last slide.
Yeah.
This previous recall this atmospheric window, you know, around the similar wavelength.
Yeah.
You see the contribution of the impact of atmosphere window.
Yeah, let me show you. There's another, I think I have right there.
Yeah.
Perfect. You set me up just right. So these are the atmospheric windows that are really kind of pertain to infrared, not to microwave. The microwave, they're out here and they're very transparent, but here at 4 micron, so when that black curve goes near the top, this is the total, then it's 100% transmittance. And at 4 micron, it's attenuated some, but it's not as attenuated as the 10-11 micron range. Does that make sense? Right? That's what you were. This is just the transmittance of the atmosphere. How clear is the atmosphere? How much of 4 micron that came off the surface of the Earth? How much of the 4 micron? What fraction of the 4 micron made it to the top of the atmosphere? And in this case, 80 to 90% of it made it to the top of the atmosphere. Okay, because that's transmittance 80-90%. Here, only about 65, 70, maybe 70%, 75 made it to the top of the atmosphere. So the 11-12 are more strongly attenuated, and most of that's caused by water vapor. So they say that the atmospheric correction for SSTs, the infrared SSTs, the big thing to correct for is water vapor and its ability to attenuate the transmittance of the 11-12, especially micron radiance up to the top of the atmosphere for the satellite to detect. So yeah, one of the advantages of the 4 micron, amongst other things, is that it's very, very clear at those wavelengths. So atmospheric corrections at 4 micron aren't as critical as they are at 11 and 12. Yeah, the important thing, and this is a little bit of hand waving because I only have so much time, and I'm not really an algorithm, pretty strong algorithm person in ocean color, but not SST. But I just want to point out that this attenuation at, say, 11 microns versus 12 microns, there's a difference in the sensitivity of water vapor. And at the 11 micron is, you know, if you added more water vapor to the atmosphere, it's gonna respond and attenuate stronger than at the 11, then it's gonna respond at the 12. So it's called the split window algorithm. And it's based on this idea that one of the bands is more sensitive to water vapor than the other bands, band being 10 microns or 11 microns versus 12 microns. So keep that in mind as we jump to the next slide, that there's this attenuation difference. One's more sensitive and it's going to attenuate stronger at the 11 micron than it will at the, and so if you add more water vapor, you're going to see the 11 micron attenuate more than you're going to see the 12 micron. So with that in mind, these are the algorithms that are referred to as the split window, and these are brightness temperatures, but they're really radiances, watts per meter squared per steradian in the 11 micron or the 12 micron range that have been converted to brightness temperature by that simple idea of multiplying by emissivity. So you'll see brightness temperature, all these empirical algorithms, instead of seeing watts per meter squared or radiance values, you're going to see these T's, these brightness temperatures. And the 4 and the 5 mean band 4, band 5, and that means 11 micron, 12 micron radiance. Again, just heads up. You know, somebody at JPL or somebody at somewhere else is gonna be the person or group, or NOAA is gonna be the group that has to worry about these very specific things. So don't jot down and go, if I don't get this algorithm and write down and what are the coefficient, do I need a table to look up to find the coefficient values to convert so I can get SST? You are going to be given SST. Okay, so but it's good to be aware that these coefficients are empirical. They're taking matchup data with buoys, whether they're moored buoys or floating Argo floats, and they're taking those temperature measurements and adjusting those coefficients with the brightness temperature, watts per meter squared per strain, and converting the brightness temperatures. In this case, at 11 and 12 during the daytime, because you can't use 4 micron during the day. And at nighttime, you can use the 4 and the 11 and 12. So another advantage of nighttime is you have another band to do your empirical fit with and get a little bit nicer fit, in my opinion. Okay, yeah, this is the classic. This is the so MCSST. If you see this multi-channel SST, it is it's kind of the first algorithm that was put out there. And then the one that's more commonly used these days is the next one, called the nonlinear SST, NL-SST. You'll see that reference sometimes, NL, nonlinear SST. And it's the same thing. It's the difference between, it's added a little bit extra complexity here with bands. I guess the only complexity that really got added here is two. One is these empirical coefficients are, and this might be something to do with emissivity, but they're temperature dependent. So there's an external guess at what the temperature should be without direct measurements, and this could be the ECMWF, the European Center for Medium Range Forecasting. SST values that will be used to adjust these coefficients somewhat, not a lot, but somewhat, to just get a little bit tighter. And this term here is meant to adjust for the path distance over which the satellite had sort of transmit its SST, its watt per meter squared up to the satellite. So a little more sophistication to developing this, and this is really the algorithm that AVHRR. This is I mentioned before, the OISST, that's based on the AVHRR instrument. It's been up since 1981, so it's the instrument. I mean, multiple versions of that same instrument. So the instruments go up, and their average lifespan is 5 years, and they die. So AVHRR, they've always had a satellite launch, with an AVHRR instrument on it before the other AVHRR instrument died. Continuous, and groups that have focused very, very carefully on cross calibrating to make sure that one instrument didn't fly suddenly and create a complete giant offset in SSTs because they weren't cross calibrated. So there's a lot of attention paid to make sure that successive generations of AVHRR instruments are all comparable all the way across from 1981 to present. Yeah, so NL-SST is kind of the industry standard, so to speak, by which most of these infrared products are being generated these days. Okay, here you go. This is again, I have the citation here below. It's blocked out a little bit by the by the way, those folks that are remote, there is presumably a way for you guys to get, there's a couple things to say for those who are remote. Chuck, do those guys have access to that box folder for the optional reading? Okay, so if you look under that box link, there's Monger Monger material or something like that. Anyway, in there is a directory with optional readings, and most of it are things. This is one of those readings here, and it's I can't even read what I have cited here, but you'll find it in the optional reading. So the other thing I want to mention to the folks online is tomorrow when we do the when we do the computer exercise, everybody has all the software loaded on these computers in this lab, but that under that same box, under Monger materials, there's a computer exercise. And the appendix of the computer exercise has very detailed instructions on how to add all the Python stuff that you need to add to a Mac. So if you don't have a Mac, I don't know what to tell you exactly. But if you have a Mac, sometime between tomorrow, you can load all that onto your laptop, and you can follow along. And run through that exercise on your Mac pretty easily, I think. So. Okay, so this is just to say there are a lot of satellites up there, and they have a lot of different, so some of them are infrared, some of them are passive microwaves. So those are the microwaves, and there's more IRs than there are microwaves. These are geostationary satellites, and these are low Earth orbit. These are polar orbiting satellites. So it's a little overwhelming. Like someone, Chuck said, can you do the SST lecture? I kind of knew there was this wild west of different SST products, and I'm like, gulp, okay, I guess so. Anyway, it was a bit of a challenge for me to sort through some of this stuff, but I came across a nice paper that was put out in 2004 by Huang and others, and they did all the hard work, focusing specifically on their usefulness, these different products' usefulness for marine heat waves. And in reading this, finding that this daily OISST put out version 2. It's now 2.1, put out by the NOAA group, the National Environmental whatever information, NCEOI or whatever. Next or 2 slides, I'll show you where the data sources are. So this optimally interpolated OISST daily data is sort of, well, you'll see the little quote at the bottom, well, is blocked a little bit, but the National Center for Environmental Information, this is a NOAA site, the OISST V21, among the best SST products for long-term periods of relatively coarse resolution. So it's 25-kilometer resolution. So it's good for, Northeast Pacific and such. Good for many cases, maybe not, really fine scale, maybe Puget Sound is not going to be so great for. You might want higher resolution data for that, but nice for the lower resolution. It's a blend of AVHRR, so it doesn't blend the microwave stuff in with this. It's just AVHRR, and ship drifting buoys, Argo floats, all go into this data set. It's 25 kilometers, keep in mind. And then finally, you can go to these websites. There's a description of the data in this URL. There's where the data actually sets. And if you click on that link, you get to this page that has year, 1981 all the way till present. Click on a year and you're going to get month 1 and day 1, month 1 and day 2, month 1 and day 3, all the way to month 12, day 31. And you could be clicking for a long time, one by one. If you could download them all by clicking on them. But I wrote a small Python script that just loops through and pulls each one of those files over. So tomorrow, you'll open up a terminal window, you'll launch Python, you'll import this utility file that I created, and then you'll use this little function that I created in that file called wget this NCIOISST, and you'll give it a year. I want year 2021, and it'll pull all of the days for 2021 into your computer. And then this is the 30-year climatology, and this, I went to find this because I wanted to use it, for this workshop, and I got to the data website and I got to the link that said, this is the data, and I hit download and it said, data not available, contact the provider. And there was a phone number, so I called this guy, and he said, well, I don't have anything to do with this data, but I can give you the email address of the folks who are really into this. And one of the folks was Yin, and he emailed really within an hour or two. He said, here's the data. And he said, and I'm also going to make that link active for everybody. So he made the link active. If you want to down, so you don't really, this is only a handful of files. So you can get daily climatology, that's 30 years of day 1, 30 years of day 2, 30 years of day 3. Or you can get monthly climate. So month 1, month 2, month 3 of 30 years, month 2 of 30 years. So various temporal resolutions of this climatology. I just brought over the daily because that's what we want to work with in this case, I think. And so the idea is this, I think, how many people have not seen a figure that looks something like this? Everybody's seen it. How many people have seen a figure that looks like this? This is a better way to ask this, isn't it? I know that. Okay, so anyway, you say who hasn't seen this? Nobody wants to raise their hand. So kind of pose this the proper way. So anyway, so you plot the climatology, you plot the 90 percentile of the climatology, and then you plot your actual year data. And when your year goes above the 90 percentile for a period of time, that's, you know, and everybody, I guess, there must, I don't know if there's any variability in how many days constitute a heat wave. But anyway, you get the idea of basically just summing up the number of days that this curve is above the 90th percentile to give you some metric. And I'm guessing there's different metrics of how intense heat waves are, et cetera, et cetera. Again, figures here coming. Here's you're going to hear lectures from Hog Day later, but you can also infer something about the intensity of these heat waves by how far above that 90th percentile you've risen. And then last slide on this SST analysis kind of stuff that I've just been talking about. The next lecture, the third one of 3, is just, this is Unix, this is Python, and it's kind of setting you up for tomorrow. So this is the last, and this is just a, you know, I was like trying to put, you know, so I'm starting to write some Python code that's gonna like create a time. So you have a code tomorrow that will do this for any year you want. It'll do the 30-year climatology and the 90 percentile, and it'll do whatever favorite year you want for a given lat lon. And again, in the future, you can say, I want that lat lon center, but I want to take all these, you know, pixels plus or minus. And I thought, oh, maybe I'll learn about some of the, you know, somebody must have created software already that does this kind of stuff. So I started searching, and I came across these 3 analysis software. The marine heat waves in Python is the kind of the initial version of this. And then do you know who knows this software? Okay. So my understanding is like this is the original, and I don't know why they did this, but the original basically got sort of reformatted and then added to or whatever into R instead of Python, and probably refined. So the middle one, that heat waves R, is I think currently the more popular one to be using these days. Is that, for those who are familiar, is the R one the one you're using, or the Python one? Python one. Oh, okay. Anyway, I thought, seemed like when I looked at when it was the last update, this one was last updated under the GitHub, and was you know, much more recently. This one hasn't been updated for a long time. And then I came across this other one because, again, correct me if I'm wrong, because I finally said, okay, I'm done with that. I'm just going to write my own code, make some simple stuff. I have 2 hours. I don't have, you know, 2 weeks, you know, here. There's another one out there that is supposed to be a 3D version. So these 2 software take a time series of a given, you know, like a single time series. So that could be 1 lat lon pixel that you pulled out of your time series, and that's going to be analyzed to the nth degree on how many consecutive days was it above the 90 percentile. And so if you wanted to do something like that across the whole North Pacific or the whole North Atlantic, you would have to loop through each one of those pixel locations and pull out and do that analysis and go to the next pixel location and do the analysis. And anytime you have to put 2 loops, you know, the XY loop, the row column loop, and one by one do this analysis, it's going to be like painful. And the whole idea of NumPy and Python and what it could be MATLAB is to try to vectorize that stuff and have it done, you know, all at once. And so I think this code, and they're like, this is still kind of beta, we're putting this together, please give us your comments, et cetera, but there is a an R version of the software that is trying to do something that's more akin to what MATLAB would do, or NumPy and Python, where you do it, you know, all in this kind of vectorized way. Okay, that's it for 2. And what do we have here? We have, when was I supposed to quit?
Yeah, and it might be good to actually finish a little bit before noon.
Okay,
Um,
hey, let me go. Stop. Good. We shouldn't have taken that 10-minute break after this gone. Okay, so real quick, you know, Carl Bonzo. Once, you know, I was a budding brand new grad student, and his words stay with me today is, you know, if you ever want to begin a lecture with you know, and it's true. I watched some people go, this probably isn't going to be very good, but and it's like, oh man, Carl Bonds is so right, man. That's such a so I will defend myself here, you know. So I am a traditionalist, you know, and so we are going to use a Unix terminal. We're going to use a text editor. We are not going to use an integrated integrated development environment, IDE. How many people are really into IDEs? If you can, I just knew it. So I am a slide rule kind of guy. So we're going to do the slide rule. And I'm trying to always like figure out, how do I argue my way that I'm right and everybody else is wrong? So part of it is, you know, like there's all kinds of these IDEs are running around, and how am I going to write the instructions on pull down this and click on this for every possibility? So this is like the simplest thing. You can't go wrong with this. So that's my argument. And also it's just that I've been doing this since before. Yeah, my first programming was basic on an Apple IIe before the Macintosh ever got made. So to give you some idea. So anyway, we're going to work with Unix, we're going to work with Python, we're going to work with a text editor, we're going to write some code or run some code, and you'll see how to do it the old-fashioned way. If you haven't ever done it, it'll be instructive to you. Okay. So your Mac, you can't see it because it's stupid. This is what I hate about Zoom, is all this stuff that blocks, but there's a little icon that kind of looks like that in your toolbar. You'll click on it, open up a terminal window, and you're now in Unix. And Unix file structure is it's organized in a tree of connected or interconnected directories and subdirectories. And the base of the tree is called the root directory. Instead of calling it root, spelling it out ROOT, it's given a special character called a / that is root. So if you wanted to change to your root directory, you do cd space / and you'd be at root. So root directory, and then everything hangs off that. There's home, there's grad students and undergrads, and so you can create, you know, folders and subfolders and subfolders, if you want to call it folders, but directories, subdirectories, all the way down. And I will just point out that, because this will come up, you know, if you want to try to understand some of the code, you want to appreciate that. This is in Unix, this is the full name of a file. The full name of a file is the path. Where does a file sit? What subdirectory? How do you get to that file? And then the base name of the file. What's the, whatever, my favorite, you know, text document in this case. So there's the base name and the directory path. Those two together make up the file name. And you know, they make whole books on Unix, and all we're going to do, if you have, how many people work with Unix regularly? This is like, I love, notice how I asked that instead of saying how many people have never worked with it. So how many people work with Unix? There you go. Thank you. Good morning. Anyway, so whole books, you know, and there's lots of cool things that it can do, but in this exercise, I think you only need these 4 things. Print working. So you're on a black screen and you're like changing directories into a subdirectory, and you're like, where am I exactly? Because all you see is a black screen at this point. And pwd return, and it'll say say you're in /directory1/directory2 so you know where you're at. It's a nice handy command. And they all, by the way, they all make almost English sense, PWD, print working directory, CD, change directory. So, and again, you learn all this by muscle memory. You're not going to learn it like flashcards and stuff. So if you haven't used it, there's these 4 commands you're going to use. And in the handout tomorrow, it says type CD space. So no problems. This is kind of important, this ~/home directory. So yeah, I'm not going to go too quick so anyways, Unix originally created, still today is meant for multi-user. One computer can have lots and lots of users on the computer. Every user, when they log in, they come into their home directory, and somebody else logged in on the same computer, they would come into their home directory. So your home directory is, your favorite place because that's where all your stuff is. And so it gets a special symbol to make life easier. Instead of typing out /users/FHL guest, you can just do ~/. So if you wanted to change to your home directory, you could do CD space ~/ instead of users, blah, blah, blah. You can also cheat because there's an easy way to get to your home directory. A lot of times you'll CD down, 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 deeper and deeper. And you're like, I just want to get back to home. So if you just type CD return, then you're back at home. By the way, when I do in the handout, when I do like return, don't do forward, lesser than, return, greater than. Hit the return key or the enter key or whatever it is. So you never know. Yeah. Okay. Let's see. Oh yeah, this thing, Python does not, so Unix knows ~/. Python does not. If you write something in Python that says fname equals ~/ data, my project, and some file name, Python will not know what to do with that because it doesn't know how to convert on its own without any help. It doesn't know how to interpret ~/ as home directory. So you either need to spell out, like in this case, you need to literally spell out instead of using that little shorthand. You have to, /users, in this case, Friday, FHL guest, / data or whatever. You would have to spell everything out. Or you could keep using the ~/, but in the Python code, you have to have this extra function that will expand that ~/ into / users. Okay, just about done. Open source. This is real quick. So Python comes on all the computers native, and but there's limited functionality to that. But lots of groups have created lots of really cool stuff. That's why Python is so amazingly popular. There's lots of people doing lots of cool things, making lots of great packages. And then, many, many years ago, this is like, again, I got to live through like, hey, we've just introduced Linux, and I was like, I'm on my Silicon Graphics machine at that time before Macs got converted over. Macs didn't always used to be Unix. Anyway, Linux, and man, trying to manage Linux with all these conflicts. They'd like the glib whatever library is now in conflict with the glib library. It was just super amazingly crazy. And then finally, like Ubuntu and all these other things came along, and all of that stuff went away. And early on with Python, I was teaching my remote sensing summer workshop in IDL. It's like MATLAB, and it's what NASA used really extensively. But I started to introduce Python, and one of the undergrad PAs was really Python literate, and he did an all-nighter. I said, install the Python packages, and he spent all night trying to resolve the conflicts. I added netcdf, package, but that conflicted with NumPy package. And when I tried to fix NumPy, this other thing broke. And so there are all these things that have to interact with each other. And so a package manager, and you can't read it now because it's been blocked, but Anaconda is a really nice package manager. So you download Anaconda. That already downloads a lot of cool stuff like Matplotlib, and NumPy and everything else, but you can add to that. And to add to that, you just, so Anaconda, and then you just, then you can add, you can make packages available, let's put it that way, by creating a Python environment that has all sorts of added packages that you want. It could be well, it could be netcdf read package, for example, and then it's sitting there waiting for use, but it won't actually get used until you import that. Once that sits in the background in your environment that this package manager deals with. And then when you write a program, you're like, I'm going to be needing netcdf read, so I'm going to import that into that particular program. So each program can add the features. I call it like the Matrix, where Keanu Reeves, says, I need to learn how to fly a helicopter. And they upload. I can fly a helicopter. So your Python program, it's like, I know NumPy, or oh my God, I know netcdf. So as soon as you do import, suddenly the Python knows all this cool stuff, just like Keanu. Two ways to run Python. You're going to do both ways tomorrow. One is open up a Unix terminal and type Python return. You're in Python at that point. You'll see these three little. Next slide, you'll see it, but you'll be able to. Well, you'll see it right there. That tells you you're in Python, so you can write all the Python commands at that terminal window, at that prompt, that that arrow. And that's really cool if you have like one little function, and you want to figure out how it works. You can just open up, launch Python, and make some kind of quick examination of how that function that's new to you works. But if you're going to write some elaborate thing that does all kinds of elaborate things with lots of lines of code, you're going to want to write it in a text file, and then have Python interpret that text file. So you do Python at the terminal window. Once you write all the text into a text file, you don't have to call it .py, by the way. You could have called that nothing, or you could have called it .txt. But if you did Python space and the name of that text file, it's going to go through each one of those lines of code in the text as if you were typing them and run the code. And that way you can, one, debug the code because you didn't have to rewrite everything again. And two, you can save it and come back to it later, etc. We have just a few more slides, I swear.
Well, no, but I think we want to head out of here no more than 3 minutes because
Okay.
we want to get
I'll be done.
ahead of the line. Okay.
I'll be done. Okay. You're going to see there's two things open: terminal window and a text editor. You're going to write your code in the text, save it, and then over there you're going to save Python space, name of my text file, and you're going to run it, and it'll do whatever you want. Import. So these are the things that you import. This is how you'll see stuff at the top. This is where Anaconda's made them available for you to import if you want. And then when you're writing code that specifically needs it, you can import it into your code and use it. I'm going to skip that. You can read about it. And then, has everybody worked with something like MATLAB where you can add two 2D arrays together? Who's worked with that where you can take 2D array 1, 2, and add them together? Okay, then I'm not going to talk about it. And then finally, reading, this is the last slide, reading netcdf files. There's a function that actually comes with Anaconda without adding anything extra, called netcdf ncdump. And the -h is just the header information, not all the data, because that would be like the matrix flying by with all the numbers. And it'll tell you lots of information. Importantly, a lot of satellite data products come scaled, and you need to scale them back to degree C. And so you need to read the metadata and find out whether it's been scaled or not scaled. In the case of the SST, the OI SST, it's scaled. You have to multiply by 0.01 or you will have the wrong centigrade values for that. And then once you get that, you can, there's a function that I wrote called read CDF product, and you'll use that and run that tomorrow. And then I'm just done because that's not necessary. So we're done. Let's go. Stop everything. Stop recording. Thank you guys online.
I'm gonna leave like. What's that?